So now it's my pleasure to introduce our speaker today. Professor Karin Öberg is a professor of astronomy and the director of the Öberg Astrochemistry Group at Harvard University. Dr. Öberg completed her PhD in 2009 at Leiden University. Her work focused on laboratory and observational work on gas-grain interactions during the star formation process. She is an expert on astrochemistry and its impact on planet formation, including the compositions of nascent planets. These topics are addressed using a combination of laboratory ICE experiments, spatially and spectrally resolved millimeter observations, and theory. For her work, she was recently named a 2020 Simons Investigator. Today, Professor Öberg will be talking about high-resolution chemistry in planet-forming disks. Without further ado, I now can turn the control to Professor Öberg.
Thank you so much, Brenda, for that lovely introduction. And thank you, of course, for having me to speak here today. So most of what I'll be talking about today is how we use ALMA to really map out the environment where planets are forming, and especially their chemical environment. So we know that planets form in these disks of dust and gas around young stars, and we know that there's molecules there. And we think that there are several ways in which these molecules, these chemical structures, impact the outcome of planet formation. But before continuing on with the science, since I do want to end this talk with a few questions, I want to start with just acknowledging my group, the sources of funding that has made the science possible that I'll be presenting today, and especially the many young people who are really responsible for, I would say, 90% of the results that I will be presenting today. So just a shout out to the amazing astrochemists that I have had the privilege to be working with. But back to the scientific questions. So there are two things that motivate my research in general, but more specifically what I'll be talking about today. One is to understand our own solar system and see if we can build up a bit of an interpretive framework for how and where and why the solar system assembled the way it did. The other one is maybe not surprisingly related to the amazing discovery in the past decades that exoplanets are everywhere. And while we don't know that much about them yet, they are certainly something that fascinates us and something we will, and objects that we will be able to predict what they are made of, whether they're likely to have water and organics on their surface, or if there are giant planets, if they are similar to our Jupiter or not. So more specifically, to tie these questions together to these disks that I will be talking about, I'd say the fundamental idea is that if we know the distribution of material in these disks very well, and if we know where in these disks planets form, we should be able to predict what their compositions are. So that's the sort of predicting, for example, exoplanet compositions way of thinking about the problem. On the other hand, if we still know our disk very well, and we know a planet's composition very well, we should be able to backtrack where it formed. So as long as you have sort of 2 out of 3 of those, you should be able to predict the third. It's sort of the fundamental part, like what's going to tie this talk together. So 2 things that I want to talk about. How can we get clues to where and when different kinds of planets form? And how do we know what the chemistry is like in these disks and how it evolves both over the extent of the disk and with time as planets are assembling. So let's start with the first questions, like how we can use our chemical understanding of these disks to say something about where planets form. So I think prior to exoplanets, I think we thought we knew roughly what kind of planets form. This is a cartoon of our solar system. And if we look at papers sort of pre-finding hot Jupiters around other stars, the basic assumption was that planets formed roughly where they're sitting today. So Jupiter formed at 5 AU, let's say, give or take a couple of AU. Now we have evidence for that probably not all planets form where they're currently sitting inside of our solar system. And then the question comes, can we, based on their composition, get some clues on where they originated? In our case, in the solar nebula, in the case of exoplanets, in planetary disks around other stars. And I would claim that we can, and that Jupiter is a very good test case for this idea. So Jupiter has a very odd composition. So this shows you can think about this as the concentration of elements in Jupiter compared to the sun. So if Jupiter was like the sun, then all the elements would fall along this red line, so oxygen, carbon, nitrogen, sulfur, and so on. But instead, all of them, except for oxygen, and oxygen is probably a mismeasurement, and I'll come back to that in a few slides, seem to be enhanced by about an extra factor of 2. So you have a concentration that's at 3 instead of 1 when we come to comparing Jupiter to the sun. So this might not seem odd at first, but I will explain why it is, based on how we think that Jupiter formed. So the most common theory of how a gas giant forms is that you first form a core that's made out of solids, then you accrete a big envelope out of nebular gas. That nebular gas is probably approximately solar. And then you pollute that envelope with solids, either leaking from the core or being accreted from pebbles, planetesimals, impacts, giant impacts, whatever solids you can get hold of. So it's not weird that Jupiter is enriched in these heavier elements compared to the sun. That we can explain with this large step of core mixing or pebbled like dissolution in the envelope. What is weird is that it's enriched in all the elements the same way. And why that is and what that has to do with disk chemistry, I'm going to try to explain with this illustration here, which shows that as you go away from the sun in the solar nebula, it gets colder because you're further away from the sun. And that means that volatiles start freezing, more and more volatile molecules start freezing out onto grains. So you change your solid composition, and you change your solid elemental composition as you step outside in the disk. So if you're sitting at 1 AU, you will freeze out water, but you have to go all the way to 30 AU to freeze out N2. So what compositions do these polluting solids have if we're sitting at 5 AU? Well, all phosphorus and sulfur will be frozen out, most oxygen, some carbon, but basically no nitrogen or noble gases. So if Jupiter formed at 5 AU and got its solid pollution at 5 AU, you would expect a composition of Jupiter looking like this. So lots of sulfur and phosphorus, not so much carbon, and very little nitrogen. On the other hand, if you move Jupiter's formation zone to, let's say, 35, 40 AU, then everything is frozen out, which means that your polluting solids now have solar composition, have a uniform solar composition, and enrich, give it a constant enrichment to whatever level that it just depends on the amount of solids that becomes dissolved in the envelope. So this maybe sounds a bit wild to form something like Jupiter this far out. And forming the whole of Jupiter maybe is a bit wild that far out, but there is sort of a compromise that you can do, which is that you form the core out at 40 AU, and then as you accrete your envelope, you spiral inward, and maybe even get some few planetesimals at 5 AUs that changes your composition a bit. You can tolerate that as long as you got the majority of your solids coming from the core originating at 40 AU, dissolving into the envelope. So this is an idea. Do we have any evidence that this is a plausible idea, except for this chemical argument that I just gave? I would say that we do. I mean, one of the amazing discoveries in the past few years is that disks around other stars, so analogs to our solar nebula, are full with structure, full of gaps and rings, at least some of which are presumed to be due to planets forming right now. They can be explained if you say put the Neptune-sized planet in one of these gaps, which is basically a Jupiter core. And if you look where these gaps are, they're pretty far out. So, and I mean, these disks are not normal. These are the big disks, but this shows that starting planet formation far out may not be as strange as we would think just looking at what this solar system looks like today. So this idea builds on the assumption that we know something about the disk chemical structure where planets are forming. So what I want to do now is just completely switch gears and talk about how we can use millimeter astronomy and maybe one day centimeter astronomy to map out what the chemistry is like in these disks and actually anchor the rather simplistic model that I presented to you a couple of slides ago. So ALMA has been absolutely amazing at allowing us to map out where different molecules, where different chemicals are in disks, including the organic molecules that we might be extra interested in from sort of an exoplanet origins of life point of view. We have seen quite a few organic molecules in disks, most of them with ALMA, including the 4 major families of organic molecules that we in general see in space. So hydrocarbons, nitrogen-containing organics, sulfur-containing organics, as well as oxygen-containing organics. Perhaps extra exciting is that among these organics we have detected is hydrogen cyanide, which for those of you who remember any of your high school chemistry classes, you might remember that this is not a great molecule to have around if you are a living complex creature such as ourselves. But it is a really excellent molecule if you want to get the complex chemistry started on a planet. So one of the most popular origins of life chemistries right now is the one that's outlined here in cartoon form, where hydrogen cyanide together with UV light and some source of sulfur really gets you all the building blocks very efficiently, all the building blocks of life as we know it here on Earth. And what's amazing about this chemistry and what's making me very hopeful about it is it actually doesn't get you that much else. We generally don't have a problem in creating a lot of organic complexity in different sort of prebiotic scenario. I would say we have had a big problem in creating the right ones and not then 100 times more of things that we don't know what to do with. So hydrogen cyanide seems to be one of these key molecules when we're thinking about prebiotic chemistry. And as I said, it is one of the ones we are detecting in disks. And this shows an example of maps of hydrogen cyanide in a number of nearby disks. You can see that doesn't look the same in all the disks. So even if so the good news, I guess, is it's there. It's always there as far as we can tell. What's complicating it a bit is that sometimes it shows a nice smooth distribution. Sometimes there's a giant hole right where we think planets are forming, which is maybe less helpful for getting organics onto those planets. But as I said, hydrogen cyanide is far from the only organic we are detecting. Here also shows the background continuum that we're seeing, as well as another small organic, C2H, and a CO isotopolog. So the second thing that I want you to notice is that if we look at the single molecule, we get some differentiation between disks. If we look at the single disk, and you can take any of the ones, especially over to your left, we see that the disk looks quite different in different molecules. And this tells us a couple of things. It tells us that the organic inventory changes as you go away from the center of the disk. It also tells you that the elemental ratio changes in the gas as you go away from the star, since we do know that at least C2H is quite sensitive to the carbon to oxygen ratio. So we can also use these molecules to trace how this elemental ratio in the gas changes, and then that should be related to the elemental ratio in the solids, which would tie us back to the beginning of this presentation when we're thinking about what are the solids made of at different radii in these disks. We do see more complex organics as well. These are a couple of the most complex ones detected, methyl cyanide and HC3N. We don't see anything much more complex than this, and I want to come back to this at the very end of the presentation, what to do about this, that we, even with our best efforts, have a quite incomplete inventory of the organics in these disks. So if I was to sort of summarize where we have gotten so far, it is first of all that we have a lot of molecular inventories of disks, and we see a rich chemistry that seems to be, as far as we can tell, always there. When we see a disk that is bright, we see a rich chemistry in it as well. Many of the molecules, as I just showed you, are the kind of organics that we're interested in from an ordinance of life point of view. And some of them are also good tracers of elemental ratios. And they have shown us that these ratios are not always the same, both between disks and across disks. And finally, we do see substructure. So, I mean, I showed you the spectacular D-sharp figure a few slides back showing substructure in dust. We do see some substructure in the molecules that we are looking at as well. But I do want to note that while D-sharp went down to resolutions of a few AU, we have so far been limited to scales, so let's say 30 AU or so, so barely getting into the part of the disk where we think most planets are forming. So this is awesome, right? I mean, just the fact that we can map out molecules in disks that are hundreds of light years away is already quite amazing. But especially this fact that we have been staying at these scales of, let's say, 30 to 100 AU so far, means also that we still don't know that much about the chemical structures of these disks that's directly related to planet formation. And if we want to really turn sort of a disk chemistry into a chemistry of planet formation, we're going to have to zoom in on the scales where we see the kind of substructure in dust that is shown here, and I also showed you the full gallery a few slides back, and try to understand what links are there between chemical and dust substructure. Does chemistry cause some of this substructure, or does these rings and gaps change the chemistry as the planet is assembling? When we're talking about the organics, what is the inventory actually in the inner part of the disk where we think most planets are forming? These elemental ratios, how do they change again around those, along those inner 30 AU? And finally, even though these dust images might make you think that these disks are basically pancakes, in reality, there are 2D structures. And this is seen in scattered light here, for example. And when we do see molecular emission, we do want to know if it's coming from the surface or if it's coming from the midplane where planets are actually forming. So these are all questions that we're going to have to deal with if we're going to tie the planet formation and the chemistry we're observing, if we're going to be able to tie those together. So trying to tie those together was the motivation for a large program that we are currently in the middle of with ALMA, so molecules with ALMA on planet-forming scales, or MAPS, where we're setting out to look at 5 disks, actually the 5 disks that I just showed you, in 20 or so molecular lines, down to scales of 1/10 of an arc second, which corresponds to around 10 AU for most of the disks we're looking at. Most of the work that I'll be showing in the next few slides is the work of a graduate student, Charles Law. And the second thing that I want to say about the next few slides is that This is unpublished, embargoed material, so please be respectful, because I really wanted to get the chance to show this sort of first raw results to you. So what do disks look like in different molecules when you zoom in on them at sort of 0.1 arcsecond scales? Well, the answer is that they look in many, many different ways. And instead of having one disk, we have 20 different disks in some cases, just by looking at the same object in different molecular lines. This is maybe seen better when we look at the single molecule in our 5 disks. Picked hydrogen cyanide, it's a nice molecule. And you see that the distribution is far from the same in these different disks. Now, this might not be too surprising if you paid attention to what the disks looked like in their dust or continuum. They looked quite different. What's maybe more surprising is that if we look in a single disk and 5 different molecules, we again get 5 completely different structures. This is also seen if you just take a cut through them and look at the radial profiles. They just look very different. We see up to 4 rings in individual molecules towards these disks. So I said that one of the things we wanted to do was to link this chemical substructure to the dust in these disks. So this next set of arrows shows where there are gaps in the dust in this particular disk. You see in the case of CO, there seems to be some correspondence between what's going on in the dust and the gas. But if you go to C2H, sometimes a dust gap gives you a molecular peak, sometimes a molecular gap, and sometimes there's no obvious connection whatsoever. So figuring this out is, one of our main tasks in the next few months, what actually the link between the dust and the chemistry is. The other thing that I briefly wanted to touch upon is that if you look carefully at the data we have, you can actually get the 2-dimensional structure of the disk. So this shows so-called channel maps where each panel shows the disk, in this case in CO, and at a different velocity. So you actually see the Keplerian rotation in this case, in this disk. And if you look carefully, you'll see that some of the emission is coming from the front of the disk and some is coming from the back. And we can use this to map out from which disk height different molecules, different molecular emission originates. So if you look at CO, again, just in one disk, we see that the main isotope log comes from pretty high up in the disk, showing the height versus the radius. 13CO, a bit deeper into the disk, C18O from the midplane, which is roughly what you would expect just from the different opacities of these lines. Now, what's pretty cool because these lines are optically thick, we can use their emission to map out what the thermal structure is of these disks, which is what's shown here. So purposefully without the scale, because we're still figuring out what the absolute scale is, but red is hotter, obviously, and blue is cooler. You can see, as you expect, you get cooler gas as you go outwards and as you go towards the midplane in the disk. The other thing we can do with this data is to tell from which disk height molecules are originating, that we're interested to know whether they are part of the feeding gas of a planet or not. So showing hydrogen cyanide here and then overplotting the height of a radius of 0.1, which is, I think, a defensible definition of the midplane. You can see that the emission in the inner 1.5 arcsecond is actually coming from fairly close to the midplane and should be relevant for when we model the chemistry of planet formation in this disk. So the final thing I want to do is to stay with this inner part of the disk, where we now know that the emission we're seeing is actually coming from fairly close to the midplane, and just see whether we can see any structure there. So how you define the inner part of the disk? There's no really generally accepted definition. I've decided that the CO snowline may be as good of one as any. So that's what I picked here as to separate the inner from the outer disk. And when we look at that part of the disk, we do indeed see that we are resolving molecular structure even in this inner sort of planet forming part of the disk. And it does look quite different, both the structure and the absolute amount of, in this case again, hydrogen cyanide that we see in these different disks. So these results and many others we are currently trying to put together into a pretty large batch of papers. So keep your eyes open in the coming months to half a year, I think is realistically when this is going to appear. And I think we will really be able to start addressing some of the questions that I set out a few slides ago. But even if this is the success that I hope it is, and even if we get a lot of time to follow up this program with ALMA, there's going to be several outstanding questions that I don't really know how we're going to get to. And they say, I don't think we'll get to them with ALMA. And those are the ones that I would like to end with. One is that with ALMA, we can see molecules in complexity up to methyl cyanide and methanol in disks. This is very small compared to other sources in our galaxy. And how do we know what the actual organic reservoir, what that is in these disks? How can we find that out? Or do we have to rely on theory, or are there observations that we could potentially carry out to get to those at least one level more complex molecules? The other big, I would say, chemical mystery is nitrogen. So currently we're tracing nitrogen with molecules like hydrogen cyanide, which we know is a minor carrier of nitrogen. And that's because with ALMA, we can't see what we think are the main carriers, which is molecular nitrogen and ammonia. And obviously ammonia would be a very interesting target for the NGVLA to see if we can get enough sensitivity to go after that in a similar set of disks. We are getting into the inner 10 AU in these disks with ALMA. It is unclear how limited we are by dust opacity in these studies. We are combining both 1 millimeter and 3 millimeter observations, which is giving us some constraints. But I would say not sufficient constraints to be certain that we are really looking all the way down to the midplane, which we think is the most interesting part of these disks. And then finally, both with ALMA and with NGVLA, we will be looking at the gas. And a lot of what we want to know about when we think about planet formation is actually the solids. And how do we connect what we see in the gas with what we think is in the solids? And here I think there's both observational and theoretical advances that we should be thinking about trying to make. And with that, I would like to stop and take any questions.
Thank you, Karin, for that excellent talk. I want to remind people that if they have questions, they can enter them into the Q&A section at the bottom, and we do have a few questions for you. So the first question was posed early in your talk, and is the HCN present where comets might be forming so that comets might transport it even if it's not present where the planets are?
Yeah, no, that's a very good question. And I would say when I first showed the hydrogen cyanide in the talk, I would have had to say I don't know. Because the key, we knew that it was out at the right radii where comets are forming, or they were the previous observations, but we didn't have any constraints of how close to the midplane it was. I think with the latest set of observations that we can say, at least in some disks, we are actually looking at hydrogen cyanide that is fairly close to the midplane. And there is another clue that would suggest that this cyanide chemistry in disks is contributing to that, the cyanides or nitriles that we're seeing in comets. And that is that if you compare the organic inventory of comets to that of protostars, you do have sort of excess of these nitriles in the comets compared to protostars, which would suggest that there is a contribution from this sort of nitrile heavy chemistry that we do see with ALMA, for example.
Okay. So we have a second question in a different vein. At 70 to 100 AU distance, the dynamical timescale for core accretion to form a giant is long. We assume those wide orbit giants formed via gravitational fragmentation. Would they show a different chemical signature?
No, that's a good question. And if you form it through an instability, I mean, then you should sort of sample the gas and the solids the same way. You should just get the average composition of what the solids plus gas is at these radii. We typically assume that that is solar, that when we add up everything that's in, let's say, pebbles and dust and in gas, that you get solar composition. I think what we are learning is that is probably true if you integrate over the whole disk, or at least stellar. But it's not true if you look at individual radii. Then it's going to depend on how much, for example, dust and pebbles have drifted. So I think you could come up with a scenario where you assemble tons of solids in one of these outer rings, for example, so that when you have a gravitational collapse, maybe you do get 3 times as much solids as gas. And then you should actually get a similar chemical signature because the solids out there do have this uniform enrichment pattern. So it's a good question, and I don't think we could actually tell the difference between those two.
Okay, so I'll ask a question, which is, I was curious to know whether or not, I noticed you have, I think, one deuterated molecule that you were showing in terms of the MAPS project. Can you comment on sort of where you see us going in our ability to sort of measure deuterium as a fraction of these disks? Because it's a key thing that solar system scientists use in trying to understand, say, where a comet formed in the solar system. They will attribute where it formed to its deuterium ratio. So do you want to comment on that? Do you see progress ahead for that?
Yeah, no, I think that's a very good question. So I guess just add one more piece of context from sort of an ALMA observation point of view, that the 2 molecules we often can measure the D to H ratio in is DCO plus versus HCO plus. There's your CO with a proton, and then DCN versus HCN. Well, what you want from a solar system point of view is water, which we're not going to get to. Luckily, we think that the way that water gets deuterated and the way that DCO plus gets deuterated is related, that both happens through the H2D plus ion. So if you can isolate DCO plus production in these disks that's close to the midplane, you should be able to calculate how much sort of extra like deuterated water that you can form in these disks as well. Currently, the best estimates is that for something like the solar system, that at most half of the deuterated water in our comets or anywhere in the solar system came from these disk processes, and the rest was inherited. But that's quite model dependent, and we haven't yet had that many observations of DCO plus in sort of the right places, allowing us to calibrate these models and benchmark them. So I'm quite hopeful we'll get better data on that.
Oh, great. Okay, next question. Has there been any work on how evolved the systems observed as part of this study are in terms of their morphology and the chemical enrichment of their disks?
It's a great question. It's very difficult to know the precise ages of these very young systems. Most of them are sort of 3 million years plus minus 2, which is not so helpful when you're trying to figure this out. Among the 5 disks we are looking at, one is very young, is younger than 1 million years. The rest are in this sort of 3-ish kind of range. But they are also mature, and they all have a lot of substructure, which suggests that plant formation, or at least the first steps of plant formation, is already well underway in these disks. What I think one direction that the field is currently going, which I'm very excited about, is looking at the really young disks. So the disks that are maybe only a few 100,000 years old are just forming. since it seems like if plant formation gets started before 1 million years, then a lot of the chemistry that matters is actually what takes place, let's say, at a few 100,000 years, when you have the protostellar to disk kind of transition. These are messy and difficult observations, but I think to understand how chemically evolved these objects are, we're first going to have to figure out what the youngest disks look like chemically. And I think that's the next step.
Okay. So here's a comment or a question. Perhaps I missed it, but you were going to comment on the apparent low relative abundance of oxygen in Jupiter versus the sun.
Oh, yeah, I forgot. Good question. So when we wrote this paper, the Juno results had not yet come out. So we were relying on Galileo results. So this was a probe that went into Jupiter quite some years ago, and it didn't go super deep. And it measured this very low oxygen abundance. And they think it was because it went into a dry spot where water had some, I mean, if you only take one basic measuring point, you can get unlucky. And water is notoriously difficult and sticky and does weird things. And they think it just went into a spot where there was no water, basically. Mm-hmm. Since then, Juno has sent a probe into Jupiter that went deeper. And the hope was that you would get below the sort of layer where you have this differentiation and probe more the average composition of Jupiter. They do measure a higher oxygen ratio that is actually around 3, so the same as everything else, but with large error bars. So I think it's like +4 or -2 from that was allowed by the combined measurement and model, but it's definitely not down there at sort of 0.3 or 0.4 that Galileo was measuring. It is consistent with this uniform enrichment that all the other elements showed.
Okay. Next question. If I can ask about the embargoed material, in some of the MAPS disks in 13CO, there appear to be an almost pinwheel-looking morphology where there are gaps along the radial direction. What could lead to this morphology?
Yeah, no, that's a good question. As far as we can tell yeah, I think it's true for all of the disks. We're still analyzing the data, but what you're picking up by eye is actually not the real kind of spiral effect or anything like that. It is sort of an optical effect or radiative transfer effect, unfortunately. So you wouldn't, in 13CO, you would not be able to see any spirals by eye. Those are what happens when you have a disk that's sitting, I don't know, at an angle, and you're seeing both the front and the back side, but you're not seeing it sort of in a uniform way. So it's sort of not a very good explanation, but this has been seen before if you look at papers that show CO.
Okay. So the next question, fundamental one, which organic molecule do you think gives the best assumption about the size of the disk?
So I think that there is no single size of these disks is part of the problem. So I think if you look at millimeter pebbles, you can estimate the size. If you look at micron size dust, you will get a larger size. If you look at CO, you will get yet another size. So I think it depends on what you're after. If you're after what traces the millimeter pebbles the best, HCM actually looks like it does a pretty good job in most disks. But if we're looking at what traces the gas best, that actually the full gas disk that tends to be substantially bigger than the pebbles, formaldehyde looks like it's a better, like more consistent with the CO, for example.
All right. So the next question is, are the dust grains going to be aligned by the stellar magnetic field in the inner region? And if so, would polarization observations help you see deeper?
I don't know, and I don't know. I'm sure that's a very good question. And among the people who are participating, I saw a couple of names that would be better people to ask this question from. So it's a good one. I try to stay away from polarization just as far as I can. So I have not thought about that. Sorry.
Okay. Do Saturn's abundances tell us anything about where and how it may have formed?
Great question. Unfortunately, we haven't had a probe going into Saturn, so we know much less about its abundances. And the same is true for Neptune and Uranus, which would have been other good ones to be able to play the same game with. Especially what's impossible to do remotely. So it's difficult to do anything remotely because the surface abundances don't necessarily reflect what's in the interior. We saw that with oxygen, for example, with Jupiter, and it tends to get worse the colder the planet is. But the thing that the one family of species that we think we understand that doesn't have a lot of sort of ways to participate in chemistry and therefore get stuck to things are the noble gases. And for those, you really need to have a probe going into the planet. I guess I could briefly add that it might be that some exoplanets are actually better targets for this kind of work, because if the planet is hot, it tends to be less sequestered in terms of different elements. So you might be able to actually better model a hot Jupiter in terms of its bulk abundance based on its surface abundance compared to our own Jupiter or Saturn. So until we send new probes into the outer solar system, exoplanets might actually provide better model systems.
Yeah, that sounds great. So here's a question that a few people have given a thumbs up to. Can these chemistry and dust substructures combined together be helpful to distinguish the mechanisms for the generation of the structures?
I hope so. So in addition to that, the chemistry is, I think, really important for its own sake. The other thing that it allows us to do these different molecules is tracing the gas, what the gas is doing. And there's been a couple of papers already showing that you can look at very small velocity difference in the gas that can show how gas is basically flowing into the gaps, for example. We're hoping with our now higher resolution observations and a bunch of molecules, we'll be able to say something about the size of the gas gaps and how they relate to the dust gaps, which is another parameter that hopefully should allow some constraints on what caused the formation of these gaps, since different formation mechanisms come up with different predictions of how the relative width of the dust and the gas gaps. So yeah, both by just looking at the overall structure, but also the dynamics. And that's where you can do more things with molecules than you can with dust, because you have this velocity information.
Right. So next we have a question about whether are the rings around Saturn analogous to planetary formation or disks?
As far as I understand, not. So when we're thinking about the disks around Saturn, they are more similar to the debris disks that we see. Sort of, if you want to think about the scaled down versus the scaled up version. So around slightly older stars, we do often see these disks of debris, and we think those are forming sort of from a top-down kind of sequence, while the disks that we are seeing, they start out as micron-sized dust that then grows to pebbles, and this debris disk starts out as, say, kilometer-sized bodies that break down into forming dust. And Saturn's ring would be more similar to this second kind, where you're breaking down sort of bigger bodies to form pebbles and dust.
All right. You mentioned that ALMA will not probably be able to help us answer the final questions. What kind of facility will be needed in the future to help us answer these questions?
So it's a combination. So if we're thinking about dust opacity and ammonia, centimeter astronomy is obviously where we would want to go. I think NGVLA will be sensitive enough to allow us to do this towards, I think the ammonia is what I'm the most excited about, towards a few nearby disks. If we want to have sort of humongous surveys, then we probably need to expand it even more, but it would be really good to benchmark it towards let's say these 5 disks that we picked because they were bright. When we're talking about the gas phase versus ice reservoir, I think it is going to be some combination of gas observations, and I think ALMA is doing a pretty good job with the small molecules, and James Webb, which will allow us to look at the ice, and then coupled with theory and experiments that can fill in the gaps, which we will still have after those observations. The organic complexity is an interesting one. I'm kind of hopeful that through either like super deep ALMA observations or like a really dedicated project with something like NGVLA, we will be able to push 1 carbon atom more in complexity. But I think beyond that, we are going to have to rely on benchmarked models and experiments. I think that one it's going to be hard to take too many more steps, but it would be really nice to be able to push 1 more carbon atom. So instead of 20 molecules, we have 30 or 40, because then you remove a lot of ability to fudge your model to fit the data. So I would hope that we can do some dedicated campaigns to add 1 more level of complexity, and then bring in the theory and the experiments for the rest.
All right. So there's another question about the limitations of ALMA observations. Are the limits of going below 30 AU, this is I think one from early in your talk, because of brightness temperature or because of ALMA's resolution?
Yeah, good question. So just to clarify, so with maps, we're going down to roughly 10 AU. So we have broken that sort of 30 AU barrier. It's expensive to go down to 10 AU, but we can do it with ALMA as it currently stands. To go down to sort of 5 AU would be possible in terms of spatial resolution, but for all but a couple of these lines, we would not have enough signal to noise. So I think it would be worth it for a couple of the molecules, but it's not going to be something you do like for 20 plus molecules as we did here. Mm-hmm. So if you want to do that for anything that's not CO and maybe HCO plus, you would need more dishes, more antennas with ALMA to do that effectively, or bigger ones, whichever the community think is the most worthwhile. I think a few 30-meter antennas placed at the edges of the array would be awesome.
And that's driven by your high spectral resolution that you need, right?
That's right. That's exactly right. So I mean, the big difference between doing this continuum observations and the spectral line observations, it's almost, because in the name, is that with a continuum, you can immediately combine 8 gigahertz of bandwidth as you're making your image. Well, we want to resolve these lines into, say, 0.2 megahertz or so at least. And that's a big difference in how many photons you are collecting.
Okay, we'll give one more question and then we're going to wrap. So we have a question that says, you mentioned laboratory experiments as part of your team's work. Can formation of molecules onto dust grains be tested there? Maybe it could give some insight on why different molecules show different radial dependencies in the disks when compared to dust.
I feel this is almost a planted question to advertise what I think is very important work. So if you've ever asked this, thank you. Yes, absolutely. As I said, even with all the ALMA time in the world, we're not going to get beyond, let's say, the next level of complexity, so 3 carbon atoms, and we're not going to get to what's on the dust. But you can, this is pretty unique in astronomy, that you can do laboratory experiments on these reactions and see what reactions actually work just physically or chemically. And once you have a set of those reactions and you know your disk temperature, density, and radiation structure reasonably well, you can feed those reactions into models, predict what you're going to see, and make sure that you include some predictions of things that are actually observable with ALMA to verify that the model is reasonable. And I think that's going to be how we fill in a lot of the gaps. It's also the only way to really see what's happening over time, since as I said, we actually don't have very good time resolution with these disks. We know they're roughly 3 million years. We can tell those apart from 500,000-year-old disks and from 10 million year old disks, but there's a lot of millions of years in between, and that's where models are absolutely necessary for how the chemistry evolves as planets are formed. And of course, anchored in experiments.
Thank you very much for the wonderful talk and the wonderful question and answer session. Thanks again, and hopefully we'll see you all next week for our next talk. Applause. Thank you, Karin.
Very much.